Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 18th, 2026, just yesterday. It presents a new system called Hero that combines open vocabulary vision with robust control to cut end effector tracking error by 3.2 times. The paper is titled, Learning Humanoid End Effector Control for Open Vocabulary Visual Loco Manipulation. And as we'll see later, the results demonstrate a significant leap in how humanoid robots handle everyday objects in unstructured environments like coffee shops. First, Figure 1 demonstrates the system's versatility across diverse real-world scenarios. In the top panels, you can see how the robot adapts its whole body posture to handle objects at drastically different heights. For example, it stands fully upright to grab a can of Spam at 0.87 meters, but deeply squats to reach a kettle on a low table only 0.43 meters high. The bottom row confirms this robustness works in varied environments, from cluttered offices to coffee shops, achieving an average success rate of about 84%. Well, Figure 2 breaks down the control framework that makes this possible. On the top left, the system generates a reference trajectory to guide the robot's upper body. The central diagram shows the tracking policy, a neural network that takes this trajectory and the residual error, the precise gap between the hand and the goal, as inputs. This policy then coordinates the whole body. Crucially, the right side illustrates the correction mechanisms. If the robot's base drifts, the system detects this and automatically replans or adjusts the goal to compensate. So, while Figure 2 focused on low-level control, Figure 3 outlines the complete architecture. It starts on the left with a text query, like orange. The yellow L versus M block uses vision models to detect the object and calculate a grasp pose. Next, the blue planner block generates a collision-free trajectory using CU Robo. Finally, the red tracking section executes this movement using the learned policy, culminating in a successful grasp. Alright, moving from the design to validation, Table 1 reports the real-world success rates for open vocabulary grasping. The columns compare performance on a general table at 0.74 meters versus a short table at 0.56 meters. You can see specific queries on the left, like red Coke can or orange cube, which consistently succeed 3 out of 3 times. In fact, the bottom row sums it up. The system achieved 27 successes out of 30 attempts on both surfaces, yielding a consistent 90% success rate. So, while Table 1 covered standard surfaces, Figure 6 pushes the robot into 10 broader, uncontrolled scenes. Panel A on the left illustrates these environments, ranging from a low corridor floor at 0.43 meters to a high kitchen counter. The corresponding bar chart shows that for novel objects like a kettle or green apple, the system adapts well, securing a 73% success rate overall. Meanwhile, Panel B on the right tests the robot in cluttered setups. Even when targets like broccoli or chips are jumbled together, the system successfully grasps them 12 out of 15 times. Well, while Figure 6 showed broader scenes, Table 3 quantifies the underlying tracking precision in simulation. It compares the Hero system against 2 baselines, Falcon and AMO, across 3 different surface heights. Looking at the first column for translation error, you can see that on a general table, Hero achieves a precision of roughly 2.2 centimeters, far outperforming the 8 to 11 centimeters of the baselines. The gap is even starker on the low table at the bottom, where Falcon's error spikes to nearly 23 centimeters, while Hero stays under 2, confirming the system's robustness. Wrapping up, the big takeaway is that decoupling high-level vision from low-level control effectively bypasses the need for massive real-world datasets. The resulting 3.2 times reduction in tracking error proves humanoids can finally handle precise tasks in unpredictable settings. This offers a scalable path forward for general-purpose robots. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.